Okay. The whole is greater than the part. Euclid's Elements. In context. Key figure, Euclid, circa 300 BC. Field, geometry. Before, circa 600 BC. The Greek philosopher, mathematician, and astronomer Thales of Miletus deduces that the angle inscribed inside a semicircle is a right angle. This becomes Proposition 31 of Euclid's Elements. Circa 440 BC, the Greek mathematician Hippocrates of Chios writes the first systematically organized geometry textbook, Elements. After, circa 1820, mathematicians such as Carl Friedrich Gauss, Janos Bolyai, and Nikolai Ivanovich Lobachevsky began to move toward hyperbolic non-Euclidean geometry. Euclid's Elements has a strong claim for being the most influential mathematical work of all time. It dominated human conceptions of space and number for more than 2 millennia and was the standard geometrical textbook until the start of the 1900s. Euclid lived in Alexandria, Egypt in around 300 BC when the city was part of the culturally rich Greek-speaking Hellenistic world that flourished around the Mediterranean Sea. He would have written on papyrus, which is not very durable. All that remains of his work are the copies, translations, and commentaries made by later scholars. There is a royal road to geometry. Euclid. Collection of works. The Elements is a collection of 13 books that range widely in subject matter. Books 1 to 4 tackle plane geometry, the study of flat surfaces. Book 5 addresses the idea of ratio and proportion inspired by the thinking of the Greek mathematician and astronomer Eudoxus of Cnidus. Book 6 contains more advanced plane geometry. Books 7 to 9 are devoted to number theory and discuss the properties and relationships of numbers. The long and difficult Book 10 deals with incommensurables. Now known as irrational numbers, these numbers cannot be exposed as a ratio of integers. Books 11 to 13 examine three-dimensional solid geometry. Book 13 of the Elements is actually attributed to another author, Athenian mathematician and disciple of Plato, Theaetetus, who died in 369 BC. It covers the 5 regular convex solids, the tetrahedron, cube, octahedron, dodecahedron, and icosahedron, which are often called the Platonic solids, and is the first recorded example of a classification theorem, one that itemizes all possible figures given certain limitations. Euclid is known to have written an account of conic sections, but this work hasn't survived. Conic sections are figures formed in the intersection of a plane and a cone, and they may be circular, elliptical, or parabolic in shape. Euclid. Details of Euclid's date and place of birth are unknown, and knowledge of his life is scant. It is thought that he studied at the Academy in Athens, which had been founded by Plato. In the 5th century A.D., the Greek philosopher Proclus wrote in his history of mathematicians that Euclid taught at Alexandria during the reign of Ptolemy I Soter, 323 to 285 BC. Euclid's work covers 2 areas, elementary geometry and general mathematics. In addition to the elements, he wrote about perspective, conic sections, spherical geometry, mathematical astronomy, number theory, and the importance of mathematical rigor. Several of the works attributed to Euclid have been lost, but at least 5 survived to the 21st century. It is thought that Euclid died between the mid-4th century and the mid-3rd century BC. Keywords: elements, conics, catoptrics, phenomena, optics. World of proof. The title of Euclid's work has a particular meaning that reflects his mathematical approach. In the 1900s, British mathematician John Fauvel maintained that the meaning of the Greek word for element, stoicheia, changed over time from a constituent of a line, such as an olive tree and a line of trees, to a proposition used to prove another, and eventually evolved to a starting point for many other theorems. This is the sense in which Euclid used it. In the 5th century A.D., the philosopher Proclus talked of an element as a letter of an alphabet, with combinations of letters creating words in the same way that combinations of axioms, statements that are self-evidently true, create propositions. This pictures the opening page of Euclid's Elements, shows illuminated Latin text with diagrams and comes from the first printed edition produced in Venice in 1482. Logical deductions. Euclid was not writing in a vacuum. He built upon foundations laid by a number of influential Greek mathematicians who came before him. Thales and Miletus, Hippocrates, and Plato, among others, had all begun to move toward the mathematical mindset Euclid so brilliantly formalized, the world of proof. It is this that makes Euclid unique. His writings are the earliest surviving example of fully axiomatized mathematics. He identified certain basic facts and progressed from there to statements that were sound logical deductions, propositions. Euclid also managed to assemble all the mathematical knowledge of his day and organize it into a mathematical structure where the logical relationships between the various propositions were carefully explained. Euclid faced a Herculean task when he attempted to systemize the mathematics that lay before him. In devising his axiomatic system, he began with 23 definitions for terms such as point, line, surface, circle, and diameter. He then put forth 5 postulates. Any 2 points can be joined with a straight line segment. Any straight line segment can be extended to infinity. Given any straight line segment, a circle can be drawn having the segment as its radius and one endpoint as its center. All right angles are equal to one another in a postulate about parallel lines. He then went on to add 5 axioms or common notions. A equals B and B equals C, then A equals C, and if A equals B and C equals D, A plus C equals B plus D. If A equals B and C equals D, then A minus C equals B minus D. If A coincides with B, then A and B are equal, and the whole of A is greater than part of A. To prove the first proposition, Euclid drew a line with endpoints labeled A and B. Taking each endpoint as a center, he then drew 2 intersecting circles, so that each had the radius AB. This uses third postulate. When the circles met, he called that point C, and he could draw 2 more times lines AC and BC, calling on his first postulate. The radius of the 2 circles is the same, so AC equals AB and BC equals AB. This means that EC equals BC, which is Euclid's first axiom. Things that are equal to the same thing are also equal to one another. It follows that AB equals BC equals CE, meaning that he had drawn an equilateral triangle on AB. In Latin translations of the elements, the actions end with the letters QEF, quodarat facendum, meaning which was to be done. Logical proofs with QED, quodarat demonstrandum, which means which was to be demonstrated. The equilateral triangle construction is a good example of Euclid's method. Each step has to be justified by reference to the definitions, the postulates, and the axioms. Nothing else can be taken as obvious, and the institution is regarded as potentially suspect. Euclid's very first proposition was criticized by later writers. They noted, for instance, that Euclid did not justify or explain the existence of C, the point of the intersection of the 2 circles. Though apparent, it is not mentioned in his preliminary assumptions. Postulate 5 talks about a point of intersection, but that is between 2 lines, not 2 circles. Similarly, one of the definitions describes a triangle as a plane figure bounded by 3 lines which all lie on that plane. However, it did seem that Euclid did not explicitly show that lines A, B, C, and CA lie in the same place. Postulate 5 is also known for the parallel postulate because it can be used to prove properties of parallel lines. It says that if a straight line crossing 2 straight lines, A, B, create interior angles on one side that total less than 2 right angles, lines E and B will eventually cross on that side if extended indefinitely. Euclid did not use it until Proposition 29, in which he stated that one condition for a straight line crossing 2 parallel lines was that the interior angles on the same side were equal to the 2 right angles. A 5th postulate is more elaborate than the other 4, and Euclid himself seems to have been wary of it. A vital part of any axiomatic system is to have enough axioms and postulates in the case of Euclid to derive every true proposition, but to avoid superfluous axioms that can be derived from others. Some asked whether the parallel postulate could be proved in a proposition using Euclid's common notions. The definitions and the other 4 postulates. If it could, the 5th was unnecessary. Euclid's contemporaries and later scholars made unsuccessful attempts to construct such a proof. Finally, in the 1800s, the 5th postulate was ruled both necessary for Euclid's geometry and independent of his other 4 postulates. Geometry is knowledge of what always exists. Plato. Beyond Euclidean geometry, the Elements also examined spherical geometry, an area explored by 2 of Euclid's successors, Theodosius of Bithynia and Menelaus of Alexandria. While Euclid's definition of a point addresses the point on a plane can also be understood as a point on the sphere. This raises the question of how Euclid's 5 postulates can be applied to the sphere. In spherical geometry, almost all the axioms look different from the postulates set out in Euclid's Elements. The Elements gave rise to what it is called Euclidean geometry. Spherical geometry is the first example of a non-Euclidean geometry. A parallel postulate is not true for spherical geometry, where all pairs of lines have points in common, not for hyperbolic geometry, where they can meet infinite numbers of times.